Well, hello, chemistry students. Let's get started with today's lesson on the Bohr model. That is lesson 10 in your study guide. So go ahead and get that out. Turn to lesson 10, the Bohr model, and we'll get started. Now, prior to the Bohr model of the atom, the Rutherford model was the dominating model at the time. And the Rutherford model, again, as a review, put the positive charge in the center of the atom, which is known as the nucleus, and the electrons rotated or moved around that nucleus very much like planets in some kind of circular motion. However, as we explained earlier, that as these electrons are accelerating around the nucleus, they would begin to lose energy by emitting electromagnetic radiation. And as they lose energy, they begin to spiral into the nucleus and crash into it, essentially destroying the atom. All right. Well, that just doesn't happen. So there definitely is a hole in Rutherford's model. And again, Rutherford based his model on the understanding of classical physics of the day. So then enters Niels Bohr. All right. Now, Niels Bohr is a very young physicist, and he begins to tackle the Rutherford model problem. And Niels Bohr begins to wonder if the electron actually is exhibiting quantum behavior much like light does. And so Niels Bohr is going to begin to look at the Rutherford model and get rid of the classical sense of the electron. In other words, he's going to say, I don't think electrons are going to necessarily follow the classical physics laws. Instead, I think the electron is going to act more like Planck's and Einstein's quantum ideas, right? And so what he's going to do is model his ideas off of using the electron, the single electron in the hydrogen atom, okay? The hydrogen atom being the simplest atom because of its only one electron in it. And so our focus will be on Niels Bohr and the study of the hydrogen atom. And by the way, Niels Bohr is a Danish physicist, and he begins his work in 1913, and he actually develops his model and wins the Nobel Prize for that in like 1925, if I remember. All right, so let's do a kind of a diagram of what Niels Bohr was kind of thinking of. And it goes back to our staircase analogy, okay? So essentially what Niels Bohr is going to realize in his mind is that electrons do not behave in the classical sense like ramps. There's no continuous change in energy that the electron emits or absorbs. And it certainly cannot emit or absorb an infinite amount of energy. So he gets rid of this idea of continuous, and he really looks at it as a staircase. Now, he doesn't honestly use the term staircase. His approach is more mathematical, but we're going to use the staircase analogy to help us to explain some things here. All right, so I'm going to try to do my best to draw staircase here that you're familiar with. And again, in a staircase, you have steps. And so I'm going to just call this step 1. I'm going to call this step 2, step 3, and step 4. Okay. Now, the staircase is going to represent positions where the electron can possibly be at in the atom in Bohr's mind. So what Bohr's going to basically say is that electrons are going to have a quantized amount of energy. He believes that electrons cannot just have any amounts of energy, but they have fixed quantities of energy. Therefore, they are quantized electrons, okay? So in other words, he's going to say an electron can exist at what he would say step 1, or it can exist at step 2, or an electron can exist at step 3 or step 4 and so forth. But an electron can never exist in between step 1 and step 2. It just certainly cannot do so. By doing this, it is saying that the electron has a fixed quantity of energy. It can have energy at step 1. It can have an energy, a fixed amount of energy at step 2, a fixed amount of energy at step 3 or 4, but it cannot have an energy quantity in between step 1 or 2, or between step 2 or 3. And remember, our energy value is going up as we're going up the staircase. All right, so see if I can spell that right. So our energy does increase, as we've talked about before, but it's a fixed quantity of energy because the electron essentially can only be at certain fixed positions within the atom. All right, so hopefully that makes sense. We'll explore this idea further. But the biggest thing is that Niels Bohr is going to be the first scientist or physicist really to develop a quantum idea of the electron and of atoms in general, and just simply saying that electrons have fixed quantities of energy because they can only be at fixed positions or certain positions within the atom. And there are certain positions or places in the atom that electrons cannot be in, okay? All right, so essentially then, if we take the stairs and we lay them out into orbits around the nucleus of an atom, we essentially get Bohr's steps in the staircase. So similar to Rutherford's idea that the electron is rotating or circular motion around the nucleus, but the only difference is that the electron, when it is in a particular orbit around that nucleus, it has a fixed quantity of energy. And so it will never lose energy as long as it's in that orbit. It can continue to just go around and around and around without ever losing energy, okay? Now, that means that an electron then can only be at specific distances from the nucleus. It can be at what he would define as the first step, which we're going to call an energy level. In fact, is he going to use that term? So he can be at this energy level. An electron could be at this energy level or step, or at this step, but it can never be in between step 1 and 2 or step 2 and 3. In fact, is the electron can never be in between the nucleus and step 1, right? And so these essential energy levels that Bohr is going to define allows the electron to have a fixed quantity of energy and never lose energy as it is moving around that orbit, okay? Unlike what Rutherford believed, is that the electron is a circular motion around that nucleus. It would emit energy and lose energy and spiral into the nucleus. And Bohr is saying, well, essentially, it just can't do that because the electron's exhibiting quantum behavior. It can only be at specific places or specific distances from the nucleus, therefore causing the electron to have a certain fixed quantity of energy or being quantized, okay? More on this in a moment. All right, so Super important here. Some of these ideas that I want you to write down in your notes, okay? So here's our Bohr model, again, that we're looking at. And we have the nucleus of the atom, which is represented by this positive charge. Let me go back here so I can draw. So again, our nucleus, which is here, which has positive charge around it. And then we have our steps, step 1, step 2, and step 3, which are really going to be fixed energy levels or fixed orbits within the atom, okay? So step 1, 2, and 3, okay? All right, so what can we learn about the Bohr model? So according to the Bohr model, electrons can be found at only specific distances from the nucleus. And these allowed distances are called energy levels. The distance between one energy level gets smaller the further from the nucleus. All right, now if you look closely at our Bohr model here, if you look at the first energy level versus the second and third, you'll notice that the energy level distances are getting smaller or closer together. So as we're moving further from the nucleus, the distance between one energy level and another level is getting smaller or closer together. So the first and the distance between the first and the second energy levels are much further away than the distance between second and third. And so they're just, as we're getting further from the nucleus, the distance between energy levels are getting closer and closer and closer together. Okay, that's really important to understand, really important. All right. All right. So again, electrons that are closer to, the distance between energy levels gets smaller the further from the nucleus. Now, electrons that are closer to the nucleus are lower in energy. So that means if you have an electron in the first energy level, it's going to have less energy than if an electron is in the second energy level. Okay, so again, just like in a staircase, as we're moving from step 1 to step 2 to step 3, the energy is increasing. So that means at the lowest step in the Bohr model, or the lowest energy level in the Bohr model, that has the lowest energy value. And then step 2 would have a higher energy value, step 3 would have an even higher energy value, and so forth and so forth, okay? So the energy of the electron, the quantized energy of the electron is increasing from going from step to step, is what Bohr is saying. All right, electrons, because they can only be at specific distances from the nucleus, then they basically, it means that the energy of the electron is going to be quantized then, okay? This means that the electrons orbiting the nucleus in a stationary state. Now, when we talk about stationary states, we're talking about these energy levels, because you can think about that these distances are fixed, all right? This distance from the nucleus to the first energy level is a fixed distance. So this is known as a stationary state, the first energy level or first step. And the electron, as it's just orbiting around that nucleus, going around and around in the circular motion type of deal, it's not going to emit any energy at all. It's just going to be simply in a fixed energy state or quantized, okay? However, electrons can move from one energy level to another. So it can move from step 1 to step 2 and step 3, but it does so by jumps, okay? Because remember that an electron can never be found in between energy levels or stationary states. So we'll never, ever find an electron between the first and the second energy level, or we'll never find an electron between the second and third energy level. It just cannot happen. So therefore, if an electron is going to move from one electron shell or one electron energy level or stationary state or step, you want to say, it's got to jump from one step to the next without ever being in between those steps, okay? Just like the staircase. Now that's kind of bizarre to think about, and somewhat we call this quantum leaping too, is that the electron starts, let's say, at step 1 or energy level 1, and then all of a sudden it jumps to and appears in energy level 2 without ever going in energy level 1 or in between energy level 1 and 2. All right, and this is because, again, the electron is quantized. It can be in electron energy level 1 and electron energy level 2, but it can't be in between. So therefore, the electron's energy is fixed here or fixed here, okay? One or the other. And so when it moves or jumps, it jumps from here and automatically finds itself in level 2 without ever jumping here. Because if it can continuously move through this space through the atom, okay, from 1 to 2, then the electron is not quantized, and the electron would be obeying classical physics. It would be like the ramp, where it can change its energy continuously all the way to level 2, and it just can't do that, okay? It cannot be in between here because it is quantized or has a quantized amount of energy, or can only be in certain allowable stationary states or energy levels, okay? Hopefully that sort of makes sense here, which also then results in the fact that because the energy of the electron in the atom is quantized, the lowest possible allowed energy the electron can have is in the first energy level. So if I put an electron here, this is the lowest amount of energy this electron can have. And therefore, it can never lose energy because it will just stay here, and it cannot lose energy, and therefore it cannot begin to spiral and crash into the nucleus, because the electron is not allowed at all to ever be in this area, okay? It's just not allowed. It just cannot be, okay? An electron, the furthest it can be, or the closest, let's say the closest this electron can be to the nucleus is in the first energy level, and that is it. So the distance is fixed according to Niels Bohr, okay? And that would explain why the electron is never crashing into the nucleus, because of the quantization of the energy of the electron, okay, in those fixed stationary states, all right? Yay, hopefully makes sense to a certain extent what we're talking about here. All right, let's do this. Let me show you a video here. See if I can get to that. All right, here's a kind of a short video that sort of shows this using some diagrams and stuff. It might help you.
Bohr's model of an atom. In this module, you will learn about the Bohr's model of an atom. Prior to Bohr, there were a number of scientists who were working on the structure of atom. Rutherford was one of them, and his model was the closest model to the Bohr model of atom. In fact, Niels Bohr had helped to overcome the problem in the Rutherford's model of an atom. The Rutherford's model of an atom had a major drawback, that it could not explain the stability. It showed that electrons in an atom revolve around a positively charged center called nucleus. However, later on, It was found that any particle in a circular motion would undergo acceleration and thus would lose energy. So, the electron would take a spiral path and would finally fall into the nucleus, and the atom would collapse. But this does not take place in reality. Bohr said that electrons do revolve around the nucleus, but their energy remains fixed. He explained that the energy of electrons remains fixed because they are restricted to some fixed orbits. Each of these orbits is at a fixed distance from the nucleus and is associated with a fixed amount of energy. These orbits with fixed energy are known as discrete orbits or energy levels. These energy levels are represented by the letters K, L, M, N or the numbers 1, 2, 3, 4 starting from the center. So, the final model of Niels Bohr was similar to the Rutherford's model of an atom, which states that an atom consists of a positively charged center around which the electrons revolve. The only difference was that in the Bohr model, electrons revolve around a nucleus in fixed orbits with fixed energy. For his work on structure of atom, he got a Nobel Prize in 1922. Let's recap. Bohr model of atom suggested that an atom consists of a positively charged nucleus and electrons revolve around it in special orbits called discrete orbits or energy levels. The energy of these discrete orbits remains fixed. These energy levels are represented by 1, 2, 3, 4 or KLMN starting from the center. Bohr got the Nobel Prize for his work in 1922.
All right, so I was wrong. It was 1922 they got his Nobel Prize, not 1925. I just couldn't remember. All right, so hopefully that video kind of helped a little bit, visualizing the Bohr model a little bit. Sorry about that. Let's go back to our PowerPoint here. All right, so this is where we left off. So now what's going to happen is we're going to talk about how the Bohr model is going to explain the spectral lines, the emission spectrum that we talked about earlier for the hydrogen atom. Remember that when we look at the hydrogen atom through an electric current and the light that's emitted goes through a prism, that we find an emission spectrum of hydrogen that emits red light, it emits blue-green light, blue-violet, and violet light, okay? Light went off. All right, and now what we're gonna do is show how the Bohr model actually explains those emission spectrums, especially for hydrogen, okay? So few things here in your notes. Let's see here, I'm gonna highlight a couple things. So an electron may be excited, and we will use the term excited here to talk about an electron that is going to be promoted from a lower energy level to a higher energy level. Remember, it's kind of like quantum leaping or jumping, okay? As it absorbs an appropriate amount of energy or wavelength. So conversely, an electron may be relaxed down to a lower energy level from a higher energy level by emitting energy of the appropriate wavelength in the form of a photon. Okay, so keep this statement in mind as we continue on with our discussion here. All right, so what I'm going to do is draw a model that's going to be really important, and you should draw this model in your notes as well. Okay, so what I'm going to do is I'm going to take the Bohr model, and I'm going to take those fixed energy levels or those stationary states, and I'm gonna like cut them and then draw them as if I'm drawing a ladder, essentially, okay? So, and I know these aren't gonna be very straight lines, but I'll do the best I can. Getting close here, okay. So what I'm gonna call this is the first energy level, which is represented by n equals 1, the first principal energy level. The second principal energy level, n equals 2. The third, n equals 3. And the fourth, n equals 4, okay? So the first, second, third, and fourth energy level. And remember that the energy levels are getting closer together as we go further from the nucleus. Now, the other thing to remember is that energy is increasing as we're going away from the nucleus, okay? This is supposed to be an arrow. So the nucleus is going to be way down here somewhere, all right? Now, if we're looking at the hydrogen atom is got 1 electron, remember? And that 1 electron is really attracted to the nucleus being positively charged, and the electron is negatively charged. So the natural tendency is for charged particles that have opposite charges to attract one another, okay? Which is also essentially why we're going to see the loss of classical would see loss of energy and crash into the nucleus because of the attraction between the positive or the negative electron and positive proton, okay? But we know that that's not going to happen because the electron is found in a fixed orbit and does not lose energy and spiral into the nucleus, according to Bohr. So if I was an electron in the hydrogen atom, where would I want to spend most of my time? Would I want to spend it further from the nucleus or closer to the nucleus? Well, I would want to be closer to the nucleus because I'm attracted to the nucleus. I like the nucleus. I like that positive charge. So me as a negative particle, I would be as close to it as possible, and that would be the first energy level. So we would expect to find the electron for hydrogen as close to the nucleus in that first energy level as possible. Now, when an electron is in the lowest state of energy, and we know that an electron in hydrogen, if it's in that first energy level, it's in the lowest energy state that it can be in, okay? It can't get any lower than the first energy level. So when an electron is in the lowest energy state, that electron is known to be in what we call the ground state. I'm going to write that down, the ground state, okay? And we're going to use that terminology quite a bit here as we talk about the electron. So in the ground state, the electron is, again, in the lowest energy state that it can possibly be in. For hydrogen, because it only has 1 electron, that 1 electron's ground state is in the first energy level. When you have multiple atoms or multiple electrons in an atom, the ground state's a little different. Some might be in the first level, some electrons in the second level, and so forth, okay, which we'll look at later. But right now, just think the ground state for the electron and hydrogen is in level 1. Now, in order to promote this electron from the ground state to a higher level of energy, it has to absorb a specific quantity of energy that will allow it to jump from one level to another, okay? Now, it has to be a specific quantity of energy and not just any quantity of energy, because the electron can only be at levels 1, 2, 3, 4, and so forth. It cannot be in between levels, and so therefore it cannot absorb energy to allow it to go in between level 1 or level 2. So it has to absorb a specific quantity of energy. So if energy comes in, the electron, so let's say that there's some energy some source, could be light, it could be electricity, whatever. That electricity, or sorry, that energy is absorbed by the electron. And if it's the right quantity of energy, it can cause the electron to be promoted to a higher level. And so let's say this electron absorbs enough energy that it promotes itself to the third level, okay? Now, this is misleading a little bit because, again, it's not like the electron is continuously changing its energy up to level 3, okay? It immediately goes from 1 to 3 without ever being in between anything else, okay? Now, when an electron is in a state or an energy level that's higher than the ground state, that electron is known to be excited. And that's why I put those lines out there to show that this is an excited electron. You probably should write that down. This is an excited electron. Now, excited electrons do not want to stay in a high energy state for very long. Remember, where it really wants to be is as close to the nucleus as possible. So what is it going to do is it's going to immediately begin to lose energy, okay, or emit energy to go back down. And so let's say that it does lose energy to go back down to the ground state. Well, the energy that it loses is a photon of light, okay? So it's going to lose a photon. So whenever an electron goes from a higher state to a lower state, it always must emit energy as a photon. In other words, electromagnetic waves or light, okay? And remember, we're really talking about the idea that light is existing both as a wave and a particle at the same time. But in our mind, we're going to specifically think about it in terms of photons or particles, okay? So again, the electron jumps or quantum leaps to a higher level of energy. It's excited. It does not stay there very long. So it goes back down to a lower level of energy. And as it does so, it's going to emit light as a photon, okay? And that photon has a specific quantity of energy. So let's take a look at that a little bit closer now, okay? This is going to be really important what I'm about to draw here. I'm going to erase some of this here so I can draw some things, okay? All right, so get rid of our ground state. Okay, so let me draw in something here. Okay, so this energy level 1, is going to have a fixed quantity of energy. We'll call it E1. So the energy at level 1 is referred to as E1. The energy in level 2 is going to be E2. The energy in level 3 and the energy in level 4 and so forth, okay? Now, I want you to think about this. Now, when the electron is going to transition from a higher energy level to a lower energy level, it's going to emit light, right, as a photon. And that photon is going to be packaged with a specific quantized amount of energy, okay? So if I'm releasing a photon, let's say this is the photon that's emitted, okay, from this electron as it transitions back down, okay, do I know how much energy is in that photon? Well, absolutely. I know that the energy of a photon, right, energy of a photon is equal to h, Planck's constant, times the frequency, okay? So packaged in that photon is a fixed quantity of energy, okay? Now, does that fixed quantity of energy relate to what's going on with the transitioning in these energy levels? And it is, okay? This energy that's in this photon is related to the energy change. So I'm going to use a triangle. This triangle means change of energy, okay, between the highest energy level, which is level 3, and subtract that from the energy of level 1, okay? Now, the difference between energy from, this is a fixed quantity of energy in level 3 and a fixed quantity of energy in level 1. If I subtract the two, I get what is known as the change in energy between level 3 and level 1, right? Hopefully that makes sense. Well, it turns out that the change in energy between going from 3 to 1, okay, that's an arrow, going to 3 to 1, that change in energy is equal to the energy of the emitted photon. Okay? Oh, can't spell it right. Let me erase that. The photon, okay? So what I'm saying is that in order for the electron to go from level 3, energy level 3, to energy level 1, it must emit energy, the quantity of energy in a photon that's equal to the change in energy between the different levels, okay? Between like level 3 and level 1 in this case, all right? Now, the bigger the change, all right, the bigger the change, the more energy is being emitted. So if you think about energy level 4 to level 3, so what if the electron transitioned from, so the change in energy, let's say it goes from level 4 to level 3, okay? Now, we know that level 3 and level 4 are very close to one another. So would the change in energy from level 4 to level 3 be greater than, less than, or equal to the change of energy going from 3 to 1? Now think about that. The spacing between 3 to 1 is really large, whereas the spacing between 4 and 3 is really small, okay? So we would expect that the energy that's released by the electron going from 4 to 3 is going to be much smaller than the energy released from going from level 3 to level 1, okay? So this photon right here is going to emit a greater quantity of energy, or have a greater quantity of energy, than the photon for going from 4 to 3, okay? Now that's an important concept to kind of think about, okay, as we continue our discussion here. All right, so Bohr's theory is going to successfully predict the atomic spectrum of hydrogen then. When electrical energy is supplied to hydrogen atoms in a gas discharge tube, also called a spectrum tube, atoms absorb energy and the electrons are promoted to an excited energy level. Once excited, however, the electron has a natural tendency to drop back down to a lower level of energy, emitting the appropriate wavelength and energy of light. The emitted light for a given transition, is absorbed through a diffraction gradient as a bright line or emission spectrum of hydrogen, okay? So let's put that together then. All right, so what we're saying is, this diagram is really important for you to know and understand, okay? So let's talk ourselves through this. If an electron has been transitioned to level 3 in the hydrogen atom, that's not its ground state. This is an excited electron, right? Now this electron is going to transition back down to another level. So let's say it transitions back down to level 2, not to 1, but to 2. So if it moves from 3 to 2, it's got to emit energy or photon of light, okay, that has an energy range that, or a fixed quantity of energy that is the difference between the energy of level 2 and level 3, okay? So again, if I take the energy, the change in energy between level 3, which is going to have the highest quantity of energy, and subtract that from the energy of level 2, okay, I get a photon with an energy that's equal to that change, okay? Now that photon's energy then is related to the frequency of light being emitted. And that frequency of light is represented by its wavelength, or in some cases, a color. So what we see then is that the energy difference between level 3 and level 2 produces a photon of light that has a wavelength of 656 nanometers, which is related to a color of red. All right, this is the red light that we see from the emission spectrum of the hydrogen atom. So as the electron transitions from 3 to 2, it emits red light at 656 nanometers. If the electron transitions from 4 to 2, it emits blue-green. If it goes from 5 to 2, it emits blue-violet. And if it moves from 6 to 2, it emits violet light, okay? So these are the 4 colors that we see in the emission spectrum of hydrogen, all right? And it's based on these transitions. Now, the transition between level 2 and level 1 is a smaller transition than between 4 and 2, okay? So remember, 4 is up here and 2 is down here. There's a bigger space gap between the two. So therefore, when the electron goes from 4 to 2, it releases a lot more energy than going from 3 to 2 because the spacing is smaller here, all right? So again, what we're saying is the bigger the difference between the level drops, the more energy is emitted by the electron as a photon. And that's why we see violet light at 410 nanometers from 6 to 2, because that's the largest drop the electron takes. Therefore, it produces the largest quantity of energy between them, okay? So you need to know these specific transitions for hydrogen. You need to know that when the electron transitions from 3 to 2, it emits red light. 4 to 2 emits the blue-green. From 5 to 2 emits the blue-violet, and 6 to 2 emits the violet light, which explains the electromagnetic spectrum, or really the emission spectrum of the hydrogen atom, okay? Now, let's even get more into this. So, what about other transitions, right? Obviously, the electron just doesn't transition to the second level. If it does so, it emits those 4 colors of light that we talked about. Now, this is missing one color because it only goes up to level 5 and not to level 6, okay, in this particular diagram. So anytime the electron in the hydrogen atom goes from a higher level to level 2, it's emitting a color of light that we see, okay? But what if the electron transitions all the way down, say from level 5 to level 1? What kind of light is being emitted? Well, it's being emitted in the UV range. In fact, any of these transitions from 2 to 1 or 3 to 1, okay, or 4 to 1, all right, any of these transitions creates a large enough difference in energy to emit UV light. So for instance, from going from energy from 1, or sorry, from 2. Let's change this. Okay, from 2, which has the highest energy level, right? This is E2, energy 2. This is energy in level 1. This is energy in level 3, okay, right? So if I go from level 2 to level 1, the energy difference between those two levels, the energy difference, gives us a photon of light, okay, that has an energy that is at a frequency of ultraviolet light. And so that's why going from 2 to 1 emits ultraviolet light, because the frequencies of this emitted light is in the ultraviolet range. And that goes with any electron going to level 1, it emits ultraviolet light, okay? Now, this is known as the Lyman series. The visible region is known as the Balmer series, and then we have the Paschen series. And the Paschen series is like going from essentially from like say for instance in this case level 5 down to level 3. Whenever I drop to level 3, I am going to emit energy that is in the infrared region. So going to level 1 gives us ultraviolet. Going to level 2 gives us the visible colors that we see for hydrogen, the red, blue-green, blue-violet, and violet. And then going to level 3 gives us infrared light is being emitted. And then there's other series too for hydrogen, but we're not going to discuss those. We're only going to worry about what we see here, okay? And so these are the important ideas on this, all right? So I hope you kind of see how the Bohr model predicts emission spectrums of different atoms. Now, we've only focused on the hydrogen atom, but the same principle that is applied here to the hydrogen atom could be applied to other atoms as well, where an electron transitions to a higher level, and then it transitions back down. And when it transitions back down, it emits a photon of light with a specific quantity of energy. And that specific quantity of energy is based on the difference of the change in energy levels, okay? The energy change from the different energy levels, okay? I hope this makes sense, okay? So anyway, this pretty much wraps up this particular part of your discussion notes. I want to close with a couple of videos here, if I can get them to pull up here. All right, let's go. Let me try this. All right, here's one that I want to show you.
Planets, they were actually jumping between orbits, according to Niels Bohr. And so they didn't just move.
Here, let me go back just a little bit here.
Of atoms are built on those electrons. But there were problems with this planetary model. Electrons weren't orbiting like planets. They were actually jumping between orbits, according to Niels Bohr. And so they didn't just move back and forth on all these infinite number of orbits around the nucleus, giving off a smooth amount of spectrum, almost like a ladder, that an electron could be here, but it could also be here, and it could never be found in the middle. We call that being quantized. It has to be in a specific unit to exist. Now, how do you move an electron to a farther level? Well, you have to put a little bit of energy into it. So if we add a lot of energy, we could jump it up to this energy level. And as it falls back down, it's going to release a certain amount of energy. And so this is a visual or a model of what the Bohr model might look like. And so as it orbits around the center, if it receives a photon, it jumps to a higher level. If it gives off an equal photon, it'll drop down to a lower level. And so it's only existing in these quantized orbits. And this helped to explain spectra, because before the model was discovered or was put forth, people had started discovering spectra. They were looking into space, not with just a prism, but a spectroscope. So they were splitting the light into all of its different wavelengths. And they were starting to see these lines. So when you're looking at the sun, for example, which is mostly hydrogen, we saw these different series. So the Lyman series was developed by one scientist who was using spectroscopy, and he came up with an equation that explained what was going on, but you couldn't see this spectra because it was into ultraviolet. We also saw the Passion series that was showing the similar relationship, but this was in the infrared, and the Balmer series was seeing the same thing. And so what really he was explaining, let's throw the Balmer series up here, is that they were seeing these discrete units of light. And so where was that light coming from? If you look at hydrogen, well, you can see here as we move from this energy level 2 up to energy level 3, it requires a certain amount of energy. And as the electron falls back down, it's going to give off that energy. It's going to give off that light. And so the Bohr model predicted what these numbers were, and they fit perfectly with the numbers that we were seeing in the spectra. And so again, this only works for hydrogen. And so it's a good step model, or it's a good model to get you started on understanding how the atom is really put together. But did you?
All right, so I'm gonna stop kind of at that explanation, and want to try to show you one other thing here. Okay, so let me see if I can share this with you right here. Right, so this might also help to kind of see the relationships of things going on here. So as you can see here, we have an electron. So here's the nucleus. See if I can actually draw on this. Okay, so we have the nucleus right here. So this is going to be the first electron shell, n equals 1. Geez. Sometimes drawing is really not friendly here. So this is n equals 1. This is n equals 2, right? And 2, not 3. This is n equals 3. Now, oh, I did it again. Jeez. 2, gosh. Okay, and so forth. So what we're seeing is the electron, as it goes from the third energy level and transitions down to the second energy level, it's emitting a photon of light. This is a photon at 656.3 nanometers, okay, which gives us an energy of 1.8 electron volts. This would be the red light, as you can see on the spectrum here. This is the red light that the hydrogen atom is emitting, okay? What if we need to clear this. What if the electron is at the fourth energy level? Well, if the electron is at the fourth energy level and it goes down to the second energy level, then it's emitting a photon in the blue-green that we looked at. If the electron is at the fifth energy level and it goes down to the second energy level, then it's emitting a photon in the blue-violet. As you can see, we're getting more to the violet. And then if the electron goes from that, what is it, the fifth or sixth level, then it's emitting light, a photon of light that's in the violet level that we can just see violet right here in our spectrum, okay? So maybe that helps a little bit. as we're transitioning down to those levels. If we move the electron from, say, the second level all the way down to the first level here, we're emitting ultraviolet light. And you see from the second to the first, it's emitting ultraviolet. Okay, so anytime we're transitioning to the first level, it's emitting ultraviolet light. Okay. Ultraviolet light, okay? Well, what about the third level? Here's the third level. What does it emit? Well, it emits infrared light. It comes down, it's emitting infrared light all the way down. So again, what we're saying is if the electron goes from any level to the third level in the hydrogen atom, it emits infrared light. If it moves from any level to level 1, it's emitting ultraviolet light. And if it's emitting going from any level down to level 2, it's emitting visible light. Okay, so hopefully this helps. Anyway, that's it for today. That's all I'm going to show you. So study the Bohr model really well. It's an important model to understand. Okay, that's it. We'll see you. Have a good one.